Hello, chemistry. Mr. McKee here, and I want to talk to you about balancing chemical equations. So the first thing that we need to talk about is why we balance chemical equations. And the reason is because of something called the law of the conservation of matter. And it basically says that we cannot create or destroy matter. And remember, the fundamental unit of matter is atoms. So what we're really saying is that we can't make or destroy atoms. So consider, for example, this equation that I've written up here on the smartboard. We've got magnesium plus oxygen forming magnesium oxide, which is fine, except that as it is written, it is kind of a lie. In fact, not kind of, it is completely a lie. And you can see why if you look at my molecule representations here. We have two of these oxygen atoms on the left, and we only have one on the right. So I am saying with this equation that somehow I have destroyed oxygen atoms, and I do not have that ability. I can rearrange them chemically, break bonds, and form new molecules with them, but I cannot destroy them. So we've got to fix that, which is where balancing equations comes in. The way that we fix that is by using coefficients. And that's a very key thing to recognize about balancing equations is that we cannot use subscripts to balance equations. We must use coefficients. So what I mean by that is I'm going to put a 2 in front of the magnesium, and I'm going to put a 2 in front of this magnesium oxide on the right side of the arrow. And then we have a true statement. We haven't fundamentally changed the message of the chemical equation. We still have magnesium reacting with oxygen, forming magnesium oxide, but now it all adds up so that we have 1, 2 magnesium atoms on the left, 1, 2 on the right, and then we have 1, 2 oxygens on the left and 1, 2 on the right. So I used coefficients to show how this reaction actually occurs in reality. Okay? Let's just jump right into the first couple examples. I do want to emphasize in your rules that are in your booklet, this is probably the most important one. We balance the equations by using coefficients, not by changing the subscripts, because if you change the subscripts, you will have a completely new compound or molecule. So let's do our first example here. And these first couple are for equations with single elements, which is really about as simple as it's going to get. So the first step is to write down the elements that we have on both sides of the equation. And in this case, it is just magnesium and oxygen. It doesn't matter what order we put them in, but I do like to put them in the same sequence on both sides. That just makes it easier to compare things. Second step is I scan my equation and I look for obvious discrepancies in the number of elements on the two sides. So the thing that stands out to me is this 2 on the oxygen, and over here I only have 1 oxygen. So I am going to remedy that by putting a 2 coefficient in front of magnesium oxide. And now I don't see any other obvious things that need to be fixed, but to make sure, I'm going to add stuff up. So on the right side, I have 2 magnesium atoms, and on the left side, I only have 1 magnesium atom currently, so I'm going to put a 2 coefficient in there, and that's going to balance the magnesiums on the two sides. And I've got 2 oxygens on each side, so this equation is now balanced, which is to say it's a true statement. Pause the video and give the next example a try on your own. All right, welcome back. We have another equation here with mostly individual elements. We do have some compounds, though. So let's begin by writing down all the elements that we have here. Magnesium on both sides. We've got manganese, which can be easily confused with magnesium. It's Mn. And then lastly, we have oxygen on both sides. All right, now we look for obvious discrepancies in the number of elements on the two sides of the equation. the thing that stands out to me is these subscripts over here. I've got 3 oxygens on the left and 2 manganese, and I only have 1 of each on the other side. So I'm going to try putting a 3 here and a 2 here and see what that does to our numbers. And you'll notice I use the word try there. I recommend using pencils when you're balancing equations because you are going to end up having to erase things, and there is some trial and error involved in this process. So that's something really important to understand. Let's see where we're at with our accounting right now. I have 2 manganese on the right, I have 3 magnesium, and I also have 3 oxygen here because of that coefficient. On the left side, I've got 3 oxygens as well. I've got 2 manganese, and I only have 1 magnesium currently, but if I put a 3 in front of it, now I have 3. So we are all balanced, 3, 2, 3. Let's do the next example. These next couple examples are for equations that have polyatomic ions. So this is groups of atoms that function as an ion. And the trick here is that if these groups of atoms appear the same on both sides of the equation, then we can treat them just like they're one element instead of compounds. So for example, I've got a PO4 group on the left side of the arrow, and I have a PO4 group on the right side of the arrow. So I'm going to pretend that that's just an element called PO4. It's not, of course, but we can pretend. You could also break that into phosphorus and oxygen, and you could still get the correct answer, but it's just going to be more complicated. So this is a helpful tip here. In addition to the PO4, we have Hg, which is mercury, on both sides. Notice that I'm putting them in the same sequence here. We have oxygen on both sides. And lastly, we have hydrogen on both sides. Okay, so look for something that stands out. To me, the first thing that I notice is the number of mercuries and the number of phosphates are different on the 2 sides. I've got 3 on the right for mercury, so I'm going to put a 3 coefficient in front of the mercury on the left. And I've got a 2 subscript in front of the phosphate, which means there's 2 of them, and I only have 1 on the left, so I'm going to put a 2 in the coefficient place on the left. And nothing else is really obvious, so let's do some accounting here. As I said, I've got 2 phosphates on the left, and that's because the 2 coefficient applies to that. And because of this, I have 2 phosphates on the right. I've got 3 mercuries on the left, and I have 3 mercuries on the right. So oxygen is a little more complicated here. I've got 3 times 2 is 6 oxygens on the left. And I have only 1 oxygen currently on the right, so I'm going to put a 6 coefficient there and see if that takes care of things. 6 times 1 is 6 oxygens. And lastly, I need to add up my hydrogens here. So I've got 3 times 2 is 6 hydrogens here. And in addition, I've got 2 times 3 is 6 hydrogens there. That is 12 in total. And over on the right side, I've got 6 times 2 is 12 hydrogens. So I am balanced. Pause the video and try the next one on your own. Welcome back. Okay, this is another equation where we've got some groups of atoms that appear on both sides. We've got a PO4 on the left, and we've got a PO4 on the right, and we also have an NH4 on both sides, so we can treat each of those as if they're individual elements, even though they're not. So NH4 and PO4, doesn't matter which one I put first, but you should do it the same on both sides. And in addition to those two polyatomic ions, we've got cadmium and we have sulfur. Okay, look for an obvious fix. You could, if you wanted, add everything up at the beginning, but you're going to end up doing a lot of erasing if you do it that way. So it's nice if you can take care of a couple of the obvious discrepancies. So I see just one PO4 on the right, and I see 2 on the left. So I'm going to try putting a 2 coefficient in front of that PO4. And nothing else seems super obvious to me at the moment. So I'm going to do some accounting now. I've got 2 NH4 on the left. I've got 2 times 3 is 6 NH4 on the right. And I've got 2 PO4 on the right. And I have 2 PO4 on the left. Next, I've got 3 cadmium on the left, and I only have 1 on the right, so I see a fairly quick fix here, so I'm going to put a 3 coefficient there. That gives me 3 cadmiums on the right. It also gives me 3 times 1 is 3 sulfurs on the right. And I have currently just 1 sulfur on the left, so I'm going to put a 3 coefficient in front of all this. And that gives me 3 sulfurs. That also changes the number of NH4s that I have. It gives me 3 times 2 is 6. So you can erase this number here. And that is nice because that is what we had on the right. So now we have a balanced equation. Okay, moving on to our next example, different type of equations. This is a really important type of equation. Called combustion equations. Anything that burns is going to be combustion typically. This is the basic process that powers your automobile. It's the process that heats your hands when you're sitting around a campfire. So this is a very important type of reaction to understand. So the basic reaction is you have some carbon compound, and it can have a variety of different forms. It could be gasoline, it could be carbon compounds in wood, it could be methane gas, which is the equation we've got here. You're going to react it with oxygen. You're going to produce carbon dioxide gas and also water vapor. So anytime you're burning something, you are producing a little bit of water vapor, which is surprising to some folks. Okay, so we've got the combustion of methane here, which is CH4. The key to combustion reactions are usually pretty straightforward. Is first you need to recognize them, and the giveaway is you're always going to have just carbon, hydrogen, and oxygen. I like to write them in this order. I'll explain why. Just think about CHO. So look for CHO, and you know you've got a combustion reaction. So when you put them in this order, this is also going to get you balancing the oxygens last, which is a key. That should be your final step when you're balancing these equations. That's going to make it easier. So let's scan this particular equation, look for obvious discrepancies. I see a 4 hydrogens on the left, and I only see 2 currently on the right. So I'm going to put a 2 coefficient in front of the H2O there. And I don't see any other obvious fixes, so I'm going to do my accounting next. So I've currently got 1 carbon on each side. I've got 4 hydrogens on each side. 2 times 2 makes 4 on the right here. And on the right side, I've got 2 oxygens here, and I've got 2 oxygens here. So I've got 4 oxygens on the right side, but I've only got 2 on the left. However, this is an easy problem to solve because I'm just going to slap a 2 coefficient in front of the O2, and that gives me 4 on the left, and I am balanced. Okay, I think that's our only simple combustion reaction. Our last example is going to be a more complicated combustion reaction. This has got a bigger carbon compound right here. And sometimes when we have these bigger carbon compounds, it's going to create a little bit of a dilemma for us. And I'll show you what I mean by that here in a second. I'm going to give you the solution to it. So same steps. We've got CHO on both sides. That's how you know it's a combustion reaction. and we look for obvious discrepancies. I see 10 carbons on the left, only 1 on the right, so I'm going to put a 10 in the coefficient place there on the right. And I see 22 hydrogens on the left, and I only see 2 over here. So to fix that, I'm going to put an 11 in front of the hydrogen. So that's going to give me 22 on the right. By the way, this is kind of a giveaway about when you're going to have some complexity. Kind of a challenge here is when you see an odd number like this. So be heads up for those odd numbers in combustion reactions. So nothing else is real obvious right now. So let's add things up. I've got 10 carbons on the left. I've got 10 on the right. I've got 11 times 2 is 22 hydrogens on the right. And I've got 22 on the left. And currently I have 10 times 2 is 20 oxygens associated with the carbon dioxide there. But I have 11 associated with the water. So that is a total of 31 oxygens on the right currently. And I only have 2 on the left. So here's where the dilemma arises. How do you multiply something by 2 and get 31 oxygens? Well, you can't if you're using a whole number, okay? So instead, we're going to use a decimal. And you can divide 31 by 2 in your calculator, or you might be able to just do that in your head. And what it's going to take is 15.5 O2s. The problem is we can't use decimals when we're balancing equations. We always need to have whole number coefficients. But this is not a big deal because I'll show you the solution here. The first thing we need to recognize is that when there's no coefficient, that's the same as a 1. So now to get rid of that decimal, we are simply going to multiply all these coefficients by 2. And that's going to give us whole number coefficients. So this 1 right here is going to become a 2. The 15.5 is going to become a 31. This 10 is going to become a 20. And lastly, this 11 is going to become a 22. And we can do this because it's the same ratio, and I know it's the same ratio because I multiplied every coefficient by the same number, in this case, 2. Now you can always check and make sure that the ratio can't be simplified any, and in this case it can. Let's make sure that we are still balanced though, even though I know we are. We've got 2 times 10 is 20 carbons on the left. We've got 20 carbons on the right. We've got 2 times 22 is 44 hydrogens on the left. We have 22 times 2 is 44 hydrogens on the right. We have 31 times 2 is 62 oxygens on the left. And we have oxygens in 2 places on the right. So we've got 20 times 2 is 40 here. And we've got 22 here. 40 plus 22 makes 62. So you'll see all our numbers are the same and we are balanced. Final thing I want to leave you with here is practice makes perfect when you're balancing equations. These are like little mini puzzles. The more that you do, the better you're going to get at them. So get lots of reps. Make sure you do all your practice assignments. And as always, reach out if you need a little bit of help. Have a great day.